Something is happening on a moon almost 900 million miles away. A thick orange haze hides it. Methane falls as rain. Lakes of liquid gas sit on a surface where water turns to stone, and buried under miles of ice, something stranger waits. James Webb just pulled back part of that curtain, and what it found changed the questions scientists are asking. We'll walk through the chemistry tearing Titan's sky apart, the hidden ocean locked beneath its crust, and the machine that may have been running for billions of years. If you enjoy the ride, subscribe. The universe gets darker from here. Let's go. The telescope turned, and the whole solar system changed. In November of 2022, the James Webb Space Telescope aimed its mirrors at a moon orbiting Saturn. Scientists had studied this moon for decades from a distance. They knew the basics: thick atmosphere, liquid on the surface, cold beyond anything on Earth. But Webb was different. Webb could see things no instrument had ever seen from this far away, picking up individual molecules drifting in the air of a world nearly 900 million miles from the Sunday. The target was Titan, Saturn's largest moon, a place so strange that scientists had been arguing about it for years before anyone got close enough to look properly. When the first Webb data came back, the team gathered around their screens. They were searching for something specific, a molecule so unstable it normally vanishes in seconds. A chemical fragment that forms when Titan's methane gets ripped apart by sunlight and radiation. For years, scientists had believed this process was happening. They could see what went in. They could see what came out at the end. The middle step, the reaction actually happening, had always been invisible. Webb changed that. The first images also showed something moving in Titan's sky. Clouds were forming over the northern part of the moon. They were rising, changing shape, growing taller over time. On Earth, you would call that a storm building. On Titan, it meant the atmosphere was doing something active, something connected to the lakes and seas sitting far below on the surface. To understand why that mattered, you need to understand just how isolated Titan is. Saturn sits so far from the Sun that sunlight arriving there is about 100 times weaker than what hits Earth. Most moons at that distance are frozen rocks with no air, no weather, no movement at all. Titan has a thicker atmosphere than Earth. It has clouds. It has rain. It has seasons. Seeing that atmosphere do something new felt almost personal, like watching a heartbeat on a world you expected to be still. The Webb team had planned for months to make these observations. They scheduled time on the most powerful telescope ever launched, pointed it at one moon among hundreds in the solar system, and waited. The waiting paid off in ways that went beyond the original plan. The clouds were a bonus discovery. The molecule was what they came for. Between November 2022 and July 2023, Webb and another telescope called Keck observed Titan twice. The two observations together gave scientists a before and after view of those northern clouds, showing them shift and climb over several days. That kind of tracking had never been done at Titan from Earth-based or Earth-orbiting telescopes before. But here is the part that made researchers pause. The clouds were sitting directly over the region where Titan stores most of its liquid. Enormous seas of methane and ethane spread across the northern polar zone. Seeing clouds build above them suggested a direct connection between what sat on the surface and what moved through the sky, like the lakes were feeding the storm. The molecule Webb came to find was hiding in the upper atmosphere, and what it revealed about Titan's chemistry was something scientists had been waiting decades to confirm. That molecule, and what it means, is where we go next. Stand on Titan's surface and you would see almost nothing. The sky above you would glow a deep burnt orange, the color of a highway at sunset, but from every direction at once. No blue, no stars, just a thick, hazy dome pressing down from all sides. You would be standing in permanent twilight even at noon, because the haze above filters out most of the light before it reaches the ground. Titan is wrapped in a blanket of smog, the kind of smog that makes Los Angeles on its worst day look like a mountain meadow. This haze is made of complex organic molecules that form high in the upper atmosphere and then slowly drift downward, settling on everything below. It is thick enough that when early space probes photographed Titan, they saw nothing but orange, no surface features, no craters, no rivers, just a featureless ball of color. Getting through that haze required special instruments. Cassini, the spacecraft that studied Saturn and its moons for over a decade, used radar and infrared cameras to see through the smog. What it found underneath shocked the scientists watching from Earth. Titan has mountains. Some of them rise as high as 10,000 feet, roughly the same as the smaller peaks in the Rocky Mountains. It has vast flat plains stretching for hundreds of miles. It has enormous dark dunes running parallel across the equatorial zone, each one several hundred feet tall and miles long. And it has channels, carved, winding, branching channels that look almost exactly like river systems you would see on Earth from a plane. The whole surface looks familiar, and that is what makes it so unsettling, because everything familiar about Titan is built from different materials. The rivers are carved by liquid methane. The dunes are made of organic particles, dark reddish grains that built up over billions of years as molecules fell from the sky. The mountains are made of water ice, so cold and hard that it behaves exactly like granite. On Titan, water is a rock. At the surface, the temperature sits around -290 degrees Fahrenheit, cold enough that methane, which on Earth is a gas you burn in a kitchen stove, becomes a liquid. Cold enough that the chemistry of an entire world has been replaced. Everything that water does on Earth, methane does on Titan. Sunlight still reaches the surface, but barely. It arrives pale and distant through all that haze, about 1,000 times weaker than what you feel standing outside on a sunny afternoon. Despite that, the surface is active. The rivers are real. The dunes move over time. The weather cycle runs on schedule. Imagine walking across a landscape that looks like Utah, but is made of ice, organic dust, and frozen gas. The ground crunches under your feet, but the crunch sounds different because the air is 4 times denser than Earth's. You would feel the atmosphere pressing against you even as you walk, thick as a warm pool. Except nothing about Titan is warm. From orbit, those features disappear back into the haze. Webb could not see the ground directly either, but it could see what was happening in the air above it all. And what was happening in that air had been building for a very long time. Every other moon is bare. Europa, one of Jupiter's moons, has a thin wisp of oxygen that barely registers. Ganymede, the largest moon in the solar system, has almost no air at all. The moon has nothing. Dozens of moons orbit the outer planets in complete silence, their surfaces exposed directly to the vacuum of space. Titan has a thicker atmosphere than Earth. That fact alone stops most people. Titan is a moon, a smaller world orbiting a planet. It has no special position near the sun, no volcanic activity pumping out enormous amounts of gas. Saturn sits nearly 900 million miles from the Sunday. Everything out there should be frozen and still, and somehow Titan is sitting in the middle of the outer solar system with a full working atmosphere, weather systems, clouds, and active chemistry running every single day. The answer comes down to 3 things working together. Titan's nitrogen-dominated atmosphere is heavy. The molecules in it move slowly because the temperature is so low. And Titan's gravity, while weaker than Earth's, is just strong enough to hold those slow-moving molecules in place. On warmer worlds, gas molecules move fast enough to escape. On Titan, the cold keeps them slow, and the gravity keeps them close. The atmosphere is made mostly of nitrogen, the same gas that makes up about 78% of Earth's air. Methane makes up a small but crucial percentage of the rest. When scientists first confirmed how thick this atmosphere was, some of them double-checked the measurements. It seemed too much for a moon. The atmospheric pressure at Titan's surface is about 1.5 times the pressure at sea level on Earth. You would feel it if you stood there, a constant, invisible weight. This atmosphere did not appear overnight. Scientists believe it built up over billions of years. The nitrogen likely came from ammonia inside Titan's early body. As the interior heated and vented that ammonia to the surface, ultraviolet light from the sun broke it down into nitrogen and hydrogen. The hydrogen escaped into space. The nitrogen stayed. Layer by layer, it filled the sky above a frozen moon. Methane replenishes itself somehow, and scientists are still arguing about exactly how. Every time sunlight hits methane in Titan's upper atmosphere, it breaks the molecule apart. That process should drain the supply over tens of millions of years. Yet, Titan still has plenty of methane in its atmosphere today. Something is restocking it. The most likely answers involve the deep interior, possible volcanic processes pushing fresh methane upward from below. But that question remains open. The result of all this is a moon that behaves more like a planet. It has weather, it has seasons. Its atmosphere changes over the course of Titan's year, which lasts about 29 Earth years. During summer, in one hemisphere, methane rains fall more heavily. During the transition between seasons, global wind patterns shift. No other moon in the solar system does anything like this. But the atmosphere is only the beginning of what makes Titan strange. Because sitting beneath those clouds and inside those seas, something much more specific was hiding. Something that Webb would eventually catch in the act. Water on Titan would kill you if it fell on you. Imagine standing outside during a hailstorm, except the hailstones are made of solid water ice, and they hit the ground at the temperature of liquid nitrogen. On Titan, water does not flow. It does not sit in puddles. It freezes so completely, so permanently, that it becomes as hard and dense as granite. The mountains of Titan are made of water ice. The cliffs are made of water ice. The ground beneath your feet, wherever you walk on that world, is frozen water packed so tightly it behaves like rock. The surface temperature is around -290 degrees Fahrenheit. To put that in terms you can feel, the coldest recorded temperature on Earth was about -130 degrees Fahrenheit, measured in Antarctica. Titan is more than twice as cold as the coldest place ever recorded on our entire planet. At that temperature, almost everything familiar changes state. Gases become liquids, liquids become solids. The chemistry of the entire surface gets rebuilt around the only molecules cold enough to stay in their liquid form. On Titan, the liquid is methane. Methane on Earth is an invisible gas. You burn it in stoves, it leaks from pipelines. You cannot see it, hold it, or swim in it. On Titan, methane does everything water does on Earth. It evaporates from the seas and forms clouds. Those clouds produce rain. The rain falls into rivers, which carry it downhill into lakes and seas, where it sits and slowly evaporates again. The full water cycle, rebuilt from scratch using a different molecule entirely. Ethane, a molecule closely related to methane, also stays liquid on Titan's surface. The seas in the northern region contain a mixture of both. Scientists analyzing data from the Cassini mission estimated those northern seas hold enough liquid hydrocarbon to fill Lake Superior several times over, a sea of natural gas sitting calmly on the surface of a frozen moon under a smoggy orange sky. The cold also does something strange to sound. Titan's dense atmosphere and low temperature change how sound waves travel. If you shouted across an open field on Titan, your voice would carry farther than it does on Earth and arrive slightly differently pitched. The physics of that world reshapes everything, including things you would never think to ask about. Inside Titan's body, deeper below that icy surface, the temperature story changes. The interior generates some heat from radioactive decay in the rocky core. That internal warmth may be just enough to keep a layer of liquid water from freezing, even miles underground, even at this distance from the sunday. Scientists believe that warmth is why a hidden ocean might still be there. At the surface, everything is locked, still, and brutally cold. But that cold is exactly what allows Titan's strange chemistry to exist. Warmer temperatures would boil away the methane lakes in seconds. The cold is the point. The cold is the machine. And that machine runs on something that falls from the sky every day on Titan. something slow, oily, and alien. Rain unlike any rain in our world. Imagine rain that you could light on fire. On Titan, it rains, real rain, with clouds that gather and darken and release their load in heavy drops that hit the ground and run downhill. The process looks familiar from far enough away. Up close, every part of it is wrong. The rain is methane, the same molecule that fuels gas stoves and heats homes on Earth, falls from Titan's sky as liquid droplets. As it falls through that dense, thick atmosphere, it picks up ethane and other organic compounds along the way. By the time it hits the surface, it carries a cocktail of hydrocarbons, cold, dark, and technically flammable if you somehow introduced oxygen, which Titan has almost none of. The drops themselves fall slowly. Titan's gravity is weaker than Earth's, about 1/7 of what you feel standing on the ground here. A drop of methane rain on Titan falls at roughly the same pace as a soap bubble drifting downward in a still room. It floats more than falls. The thick atmosphere slows everything down, so the droplets drift in lazy arcs toward the surface. When those drops finally land, the ground does not absorb them the way dry soil absorbs rainwater on Earth. Titan's surface in many areas is covered with organic material, the same dark particles that form its dunes. Some of that material is waxy and barely absorbs liquid at all, so the methane runs off quickly, feeding into channels and rivers that carry it downhill toward the nearest low point. Scientists confirmed the presence of methane rain through both data and logic. The river channels carved into Titan's surface proved that flowing liquid had shaped the terrain over long periods. The channels are real, branching and winding the same way rivers on Earth do. Something had to carve them. Methane rain, flowing repeatedly over millions of years, is the answer that fits everything Cassini measured. The rain does not fall everywhere all the time. Titan's weather is seasonal, and the rainfall patterns shift as the moon moves through its 29-year orbit around the Sunday. Near the equator, rainfall is rare and happens mostly during transitions between seasons. Scientists have spotted what appear to be dark, wet patches on the surface after predicted rain events, regions that brightened after they dried out again. Near the poles, the story is different. The northern polar zone is soaked. Lakes and seas fill low-lying areas. Clouds form regularly over the liquid surface and cycle back into rain. The whole northern polar zone operates like a closed system, with methane evaporating, rising into clouds, and falling back down in a continuous loop. And then the rain carries something else with it. As methane falls through the upper atmosphere, ultraviolet light from the sun is breaking apart other molecules above. The fragments of that chemistry drift downward and mix into the falling rain. Every raindrop on Titan is also carrying tiny pieces of Titan's organic chemistry, the raw material of the world, slowly building up on the surface over billions of years. The rivers that carry that rain downhill lead somewhere specific, somewhere that holds a volume of liquid that dwarfs anything on Earth's surface by comparison. From orbit, Titan's surface looks like a map of somewhere else entirely. When Cassini's radar finally cut through that orange haze and mapped the surface below, scientists saw dark patches scattered across the northern polar region, dozens of them. Some were small, about the size of a typical lake in Minnesota. Others were enormous, stretching for hundreds of miles in every direction, covering areas the size of entire American states. These were lakes and seas, real bodies of liquid sitting calmly on the surface of a moon. The largest of them, a sea in the northern region called Kraken Mare, covers an area bigger than the entire Caspian Sea on Earth. Another large body, Ligeia Mare, is roughly the size of Lake Huron. Together, the northern polar seas hold enough liquid to fill one of the Earth's ocean basins many times over, though the liquid is methane and ethane rather than water. From directly above, the lakes look dark and smooth, almost glassy. The methane surface reflects radar signals differently from the surrounding land, which is how Cassini identified them so clearly. In visible light images, they appear as dark patches against the slightly lighter terrain around them. Standing at the shore of one of these seas, you would look out over a completely still, dark surface that stretches to the horizon. No waves crashing. The wind on Titan is gentle, and the dense atmosphere damps out disturbances quickly. The surface of a methane sea on Titan may be among the calmest liquid surfaces anywhere in the solar system. Rivers feed these seas from the surrounding highlands. Channels branch and merge, running downhill along paths carved over millions of years by flowing methane. Some channels are hundreds of miles long. Some are narrow and steep, cutting through ridges of water ice. Others spread out wide and shallow as they approach the lowlands, the same way a river fans out near its mouth on Earth. The smaller lakes are scattered more broadly. Some sit in what look like impact craters, round depressions that filled with liquid over time. Others occupy valleys between ridges. A few appear to have formed through a process where the ground itself dissolved and collapsed, leaving a basin that filled with liquid from below. Scientists are still studying exactly how each type formed. What makes these lakes stranger is what sits at the bottom. On Earth, a lake bottom collects sediment, mud, organic debris from plants and animals. On Titan, the lake bottom collects organic particles raining down from the atmosphere above. Thick layers of complex carbon-based molecules, built up slowly over billions of years, may sit under several hundred feet of liquid methane. Scientists have called this material something like seafloor mud, but made of organic chemistry instead of silt. That organic material on the lake floor matters enormously. When Webb observed clouds building over these northern seas, it connected the lakes to the sky in a direct way. The seas were not just scenery. They were actively supplying the atmosphere with fresh methane vapor, driving the cloud formation happening above them. But clouds building over a methane sea is only part of the story. The real question was what those clouds were doing when they rose higher into the sky. And the answer pointed towards something no telescope had confirmed over Titan's northern region before. Most of Titan's liquid sits in one place. The northern polar region holds the great majority of Titan's surface lakes and seas. Scientists studying Cassini maps found that the southern hemisphere has far fewer liquid bodies. Some exist, but they are smaller and appear to be drying out. The north is where Titan keeps its ocean. The three largest seas cluster together near the North Pole, separated by stretches of icy terrain. Kraken Mare is the biggest of the three, and extends far enough that from one shore you could not see the other. Ligeia Mare and Punga Mare sit nearby, each massive in their own right. Together, these three bodies cover a total surface area roughly comparable to all 5 of the American Great Lakes combined. Except the Great Lakes hold fresh water fed by snowmelt and rainfall. The northern Titan seas hold liquid methane and ethane, chemicals that on Earth exist only in pipes and fuel tanks. The sea is a fuel source. The rain that feeds it is a fuel source. The rivers flowing into it are fuel sources. Titan's entire liquid cycle is built from hydrocarbons, the family of molecules that humans burn for energy. That fact had scientists thinking carefully about chemistry long before Webb arrived. The organic molecules in Titan's atmosphere don't just sit still, they react with each other. They build into more complex structures. They fall onto the surface and accumulate. Over billions of years, the shores of these methane seas have been receiving a slow, constant deposit of organic material from above. The chemistry running on Titan has had more time to build than life has existed on Earth. The northern seas are also where Titan's seasons hit hardest. During northern summer, which lasts several years, more sunlight reaches the northern hemisphere and drives stronger evaporation from the seas. More methane rises into the atmosphere. More clouds form. The whole system ramps up. During northern winter, the process slows and the liquid refills from rainfall. The northern seas act as the engine room of Titan's weather machine, absorbing and releasing the energy that drives everything above. When Webb observed Titan in late 2022, northern summer was already underway. The hemisphere was warming, slowly and slightly, as it received its season's share of distant sunlight. The seas were evaporating. Clouds were forming. And those clouds were doing something unexpected. They were rising, on a world with methane seas instead of water oceans. Watching clouds climb higher above those seas was like watching the first sign of a developing storm system. On Earth, rising clouds mean the atmosphere is unstable. Heat from the surface pushes air upward, carrying moisture with it. As that air rises and cools, the moisture condenses into clouds. The same basic process, driven by different molecules at dramatically lower temperatures, was happening over Titan's northern seas. Scientists watching those clouds had a name for this process. They also had a reason to care about it that went far beyond weather patterns. Because the clouds were rising over the same region where Titan holds its deepest liquid. And something else sat beneath that liquid, something that Webb couldn't see, but that the Cassini mission had already found evidence for. 2 telescopes were watching at once. When Webb observed Titan in November of 2022, another team used the Keck 2 telescope in Hawaii to observe the same moon the following day. 2 observations, 24 hours apart, of the same world at different distances and different wavelengths. The plan was to cross-check results to make sure what one instrument found, the other could confirm. What they saw when they compared the 2 sets of images stopped them. The clouds had moved. Specifically, the clouds had grown taller. In the first image, clouds were visible over the northern polar region. In the second image, taken just 1 day later, those same clouds had risen to higher altitudes. They had pushed upward into the atmosphere overnight. On Earth, a cloud that rises dramatically over a few hours usually signals something violent building below it. Thunderstorms grow fast. Severe weather often announces itself through rapidly climbing cloud tops. The same basic physics was playing out on Titan in slow motion with methane instead of water vapor. But the shock wasn't just that clouds moved. Scientists had seen Titan clouds before. The shock was where these clouds were and what that implied. Previous cloud observations had focused more on southern latitudes or on patchy activity that was hard to trace back to a specific source. These northern clouds sat directly over the largest concentration of liquid on Titan's surface. The connection seemed clear. The seas below were fueling the clouds above. Methane evaporating from Kraken Mare and Ligeia Mare was rising into the atmosphere and condensing into clouds. And those clouds were then being pushed upward by the heat difference between the surface and higher layers of air. Scientists called this process convection. On Earth, it drives everything from afternoon thunderstorms to the major storm systems that spin across entire ocean basins. On Titan, it had been expected to exist, but confirming it over the north required catching it in action. Webb and Keck did exactly that. The significance reached beyond Titan's weather. If convective cloud systems are actively cycling over the northern seas, then the atmosphere and the surface are directly connected through that process. Methane doesn't just sit in the seas and slowly drift away. It rises, forms clouds, falls as rain, flows back to the seas. A closed loop, running continuously. A full weather cycle, operating on another world, with different chemicals, at temperatures no human has ever experienced. Scientists had suspected this for years based on surface features. The rivers had to be filled somehow. The seas had to be replenished. Webb gave them the first clear evidence that the mechanism was working right now, during this season, over the northern polar region. That confirmation carried a deeper implication. If the weather cycle is active, then Titan's atmosphere is being continuously supplied with fresh methane from the surface. The chemistry running in that atmosphere keeps going. The reactions keep building. And those reactions were producing something Webb had specifically come to find. Something tiny, something unstable, something that had never been directly detected over any world other than Earth. Heat rises. That single fact runs almost everything. On Earth, the sun warms the ground. The warm ground heats the air just above it, and that warm air starts to rise. As it climbs, it cools. The water vapor in it condenses into droplets. Those droplets cluster together into clouds. If enough warm air keeps rising from below, The clouds grow taller and taller until they become towering storm systems. The technical name for this cycle of warm air rising and cool air sinking is convection. Convection doesn't care what planet you're on. It runs anywhere you have a surface that's warmer than the air above it and a fluid that can move. On Titan, the fluid is the thick nitrogen and methane atmosphere. The surface isn't warm in any way you'd recognize. -290 degrees Fahrenheit counts as cold by any standard. But the seas are slightly warmer than the air directly above them, and that small difference is enough. Methane evaporates off the northern seas, rises slowly through the dense air, and eventually cools enough to condense back into liquid droplets. Those droplets form clouds. If enough of that evaporation happens at once, driven by Titan's slow seasonal warming, the rising air pushes those cloud tops higher and higher. Webb and Keck caught that process in progress. They tracked cloud features shifting to higher altitudes over a 24-hour window. That rate of change matched what models had predicted for convective activity over the northern methane seas during summer. The real observations lined up with the calculated predictions. That alignment told scientists the models of Titan's atmosphere were capturing something real. The importance extends beyond weather patterns on a distant moon. Seeing convection confirmed over the northern seas tightened the connection between what sits on Titan's surface and what runs through its atmosphere. The seas feed the clouds. The clouds produce rain. The rain flows back to the seas. Every molecule cycling through that loop is also cycling through Titan's chemistry. When methane evaporates and rises into the upper atmosphere, it enters a zone where sunlight and radiation tear it apart. The fragments of broken methane then react with other molecules floating around them. Some of those reactions build new, more complex molecules. Those molecules drift downward and eventually settle onto the surface, adding to the organic layer that has been building on Titan for billions of years. Convection isn't just moving weather around, it's feeding the chemistry machine. And that chemistry machine was producing something Webb came specifically to catch, something that forms only when methane gets split apart at high altitude. A molecule so reactive, so short-lived, that most instruments had never been able to grab it before it disappeared. Scientists gave it a simple name, methyl radical, two words that, by themselves, sound unremarkable. But in the context of Titan's atmosphere, detecting this molecule meant watching an entire planetary chemistry system in real time, catching the exact moment when simple methane begins its long journey toward becoming something far more complex. That molecule, and what it reveals about Titan's deeper story, changed what scientists believe is possible on this frozen world. Something was supposed to be there. Scientists just couldn't prove it. For decades, researchers studying Titan's atmosphere could see both ends of a chemical process without seeing the middle. On one end, methane, simple, stable, the dominant molecule in Titan's air. On the other end, complex organic compounds, acetylene, ethylene, heavier molecules that don't form on their own from pure methane sitting in the cold. Between those two ends, something had to be acting as a bridge. A short-lived molecule that forms when methane gets torn apart, then immediately starts reacting with everything around it to build more complex structures. Scientists had every reason to believe this molecule existed. Their calculations required it, but direct detection had always slipped away. The molecule is called methyl radical. It forms when a methane molecule loses one hydrogen atom, usually because sunlight or radiation ripped it off. What remains is a fragment, 3 hydrogen atoms still attached to a central carbon, but with one empty connection point where the 4th hydrogen used to be. That empty connection point makes methyl radical extremely eager to grab onto whatever it touches. It reacts fast. It disappears fast. At any given moment, only trace amounts float through Titan's atmosphere before they're gone. Webb caught it. The telescope detected the chemical fingerprint of methyl radical in Titan's upper atmosphere. Each molecule in space absorbs and emits specific wavelengths of infrared light, like a fingerprint no two molecules share. Webb's instruments are sensitive enough to pick up those fingerprints, even when only a tiny amount of a molecule is present. The detection was clean, clear, and confirmed by multiple checks. This was a major gap being closed. Scientists had a full picture of Titan's organic chemistry, from simple methane all the way to complex hydrocarbon compounds, with one critical piece missing in the middle. Detecting methyl radical filled that gap. The bridge existed. The process was running exactly as predicted. What this means for Titan is large. Every complex organic compound in Titan's atmosphere and on its surface started somewhere. Finding methyl radical confirmed that the starting point, the moment when methane breaks apart and begins its journey toward more complex molecules, is actively happening right now in Titan's atmosphere. The chemistry is live, the factory is running, and what that factory produces is remarkable. Over billions of years, organic molecules building in Titan's atmosphere have grown complex enough to form particles that drift down through the haze and settle on the surface. Some of those particles are chemically similar to molecules found in early biological chemistry on Earth. Scientists are careful about what conclusions they draw from that similarity. The presence of organic molecules does not mean life, but it does mean the raw ingredients are there, being manufactured continuously at a scale that covers an entire world. Imagine a planet-sized chemistry lab running for 4 billion years with no off switch. Every molecule it produces falls to the surface. Every surface the molecules land on holds that chemistry preserved in the deep cold. Titan is that lab, but the factory running in the sky is only half the story. Because below the surface, in a place Webb couldn't directly see, something far more unexpected may be waiting. The molecule was already gone before most instruments could see it. Methyl radical doesn't last. The moment it forms, it starts reacting. It grabs onto nearby molecules and transforms into something else. The whole process happens in fractions of a second under the right conditions. In Titan's cold upper atmosphere, the reactions slow down, which gives methyl radical a slightly longer window of existence than it would have in a warm environment. But even that window is brief. Scientists had known for years that detecting it would require an instrument sensitive enough to catch a signal that wouldn't stay still. Webb is that instrument. To understand how Webb managed this, think about what it means to take a photograph of something moving extremely fast. Regular cameras blur the image. The subject moves before the shutter closes. Catching a sharp image requires a camera fast enough and sensitive enough to freeze the moment. Webb's infrared detectors work on a similar principle for chemistry. They can pick up the faint chemical fingerprint of a molecule even when only a small amount of it is present, and even when that amount keeps changing as the molecule reacts away. The detection happened in Titan's stratosphere, the layer of atmosphere above the clouds but below the highest reaches of the haze. At that altitude, sunlight is powerful enough to keep breaking methane apart, and the products of that breakup, including methyl radical, float in concentrations that Webb could detect. Scientists had tried before. Earlier instruments and earlier missions had searched for methyl radical in Titan's atmosphere without getting a clean signal. The molecule was always predicted to be there. The chemistry demanded it, but each attempt came up short. Webb was the first to deliver a definitive result, one strong enough that researchers felt confident announcing it formally. What made the announcement significant was the word definitive. Scientists use that word carefully. It means the detection was strong enough, clear enough, and checked enough times that doubt essentially disappears. Methyl radical is present in Titan's atmosphere. The process that creates it is running. The process that uses it to build more complex molecules is also running. The middle step is confirmed. This matters for a reason that reaches past Titan. When scientists study any world for signs of chemistry that could be relevant to life, they don't just look for end products. End products can form through many routes. Catching the intermediate step, the molecule in the middle of the reaction, tells you the specific mechanism is working. Methyl radical is that intermediate step in one of the key routes toward complex organic molecules. On Earth, similar chemistry happened billions of years ago in a different environment, but the same basic mechanism was running. The same type of molecule was forming and reacting. Scientists can't say that Titan is following Earth's path toward life, but they can say the chemistry shares structural similarities with processes that mattered on the early Earth. That connection, tentative and carefully stated as it is, keeps Titan near the top of the list of interesting worlds, a place where complex chemistry runs continuously, on a scale no laboratory on Earth could replicate, for longer than life has existed on our own planet, and the factory building that chemistry runs on fuel that has its own mystery. A mystery Webb's discoveries made sharper, even if it didn't solve it. Titan's atmosphere is being destroyed right now. Every second, sunlight strikes the top of that thick orange haze and starts breaking apart the molecules it finds there. Ultraviolet light from the sun carries enough energy to snap the bonds holding methane together. When a methane molecule gets hit, one of its hydrogen atoms breaks loose. The remaining fragment, methyl radical, starts reacting. The hydrogen drifts upward and eventually escapes into space entirely. The Sun is not the only force doing this. Titan orbits Saturn, and Saturn sits inside an enormous magnetic field. That field traps charged particles from the solar wind and from Saturn's own radiation belts. When those particles stream outward along magnetic field lines, some of them strike Titan's upper atmosphere directly. The impact breaks apart molecules just as efficiently as ultraviolet light does, sometimes more so at certain altitudes. Together, sunlight and Saturn's charged particles act like a slow grinder working on Titan's atmosphere from the top down. Methane goes in, hydrogen escapes to space, heavier organic compounds form in the middle and drift down toward the surface. Over geological time, this process removes a significant amount of material from Titan's air. The rate at which hydrogen escapes is measurable. Cassini detected hydrogen flowing away from Titan during its years of observation. Scientists ran the numbers on how long Titan's current supply of methane would last at that rate of destruction. The answer came back in the range of tens of millions of years, which sounds long but is a short window in the 4 billion year history of the solar system. If methane keeps disappearing and nothing replaces it, Titan's weather cycle eventually shuts down. The clouds thin, the rain stops, the rivers dry up, the seas slowly evaporate, and the methane escapes into space rather than cycling back. What remains would be a colder, drier world covered in dark organic dunes and stripped of its thick atmosphere over time. That hasn't happened. Titan still has a thick atmosphere. It still has seas. The methane is still there. Something is replacing what gets destroyed. Scientists have several ideas about what that something might be. The most promising involve the deep interior, processes underneath the surface that push fresh methane upward. But that explanation leads directly into a part of Titan's story that goes far stranger than atmospheric chemistry. Saturn's radiation also does something else to Titan's atmosphere. The charged particles don't just break molecules apart, they also ionize them, stripping electrons away and creating a reactive zone in the upper atmosphere called an ionosphere. Inside that ionosphere, chemistry runs even more aggressively than lower down. Molecules form and transform at higher rates. Some of the most complex organic molecules detected at Titan were found in or near this region. The ionosphere is essentially an outer ring of intense chemistry sitting above the already active lower atmosphere. Two layers of chemical transformation stacked on top of each other, both running continuously. Below those layers, the haze particles they produce drift slowly downward. They take months to settle from the upper atmosphere to the surface. Along the way, they grow slightly, collecting other particles and building more complex structures. By the time they hit the ground, they carry chemistry that started in the stratosphere and got more complex every mile of the descent. And all of that chemistry is building towards something that has been accumulating on Titan's surface for a very long time. The clock is running, and nobody knows who resets it. Titan's atmosphere runs on methane. The weather cycle, the chemistry, the cloud systems, the rain, the rivers, and the seas all depend on methane being present in enough quantity to keep the cycle going. But every measurement scientists have made confirms the same uncomfortable fact. Methane is leaving Titan's atmosphere faster than sunlight, and seasonal cycling alone can account for. The ultraviolet light breaking methane apart sends hydrogen into space permanently. That hydrogen is gone. The carbon stays, locked into heavier organic compounds that rain down onto the surface. But the hydrogen is irreplaceable without a new supply of complete methane molecules entering the system. The atmosphere is losing pieces of itself every day, and the pieces don't come back. Scientists ran the calculations multiple times. At the current rate of methane loss, Titan's supply should run out in somewhere between 10 and 100 million years. Depending on which model you use and which estimates for the loss rate you trust, the range shifts. But every version of the calculation agrees on one thing. The methane Titan has today is not old enough to have survived since the beginning of the solar system. Something supplied it more recently. That leads to a question that goes deeper than the atmosphere. Where is the new methane coming from? The most direct answer would be from the surface lakes and seas. Titan carries enormous amounts of liquid methane on its surface, and that methane could slowly release back into the atmosphere over time. But the surface supply itself would also run out eventually. If the lakes are draining and the atmosphere is being destroyed, the whole system runs dry on a timescale of tens to hundreds of millions of years. For Titan to still have its atmosphere today, something deeper must be at work. Scientists have focused on Titan's interior as the most likely source. If Titan has geological processes that push methane upward from underground, perhaps through vents or cracks in the surface, that would replenish the atmosphere over long timescales. The most likely version of this involves cryovolcanism, a cold version of volcanism where instead of molten rock, a mix of water, ammonia, and methane rises from the interior and vents to the surface. Evidence for cryovolcanism on Titan exists, but it's debated. Some features on the surface look like they could be volcanic in origin. Some regions have topography that resembles volcanic structures seen on other icy moons. But Cassini never caught a cryovolcanic eruption in the act. The evidence is circumstantial, pieced together from surface shapes and models rather than direct observation. The alternative is that Titan carries a reservoir of methane locked inside its rocky and icy interior, left over from when the moon formed billions of years ago. That reservoir could be slowly leaking upward, too slowly for any spacecraft to measure directly, but fast enough to keep the atmosphere supplied over geological time. Webb's detection of active methane chemistry in the upper atmosphere made this question more urgent. The chemistry running in Titan's sky requires continuous fresh methane input. Whatever is supplying it is running right now, today, on a world nearly 1 billion miles away. And the most dramatic possible source of that supply sits not on Titan's surface, but deep below it. The equator of Titan is covered in waves, not water waves, not sand dunes, the way you'd picture them in a desert. These ridges run for hundreds of miles in parallel lines, each one several hundred feet tall and miles wide, stretching from horizon to horizon across Titan's middle latitudes. From above, the pattern looks like a massive fingerprint draped across the surface of the moon. These are Titan's dunes, and they're made of something that doesn't exist in any desert on Earth. The material that builds them is organic, dark, reddish-brown particles built from complex carbon-based molecules that formed in Titan's atmosphere and fell to the surface over billions of years. Scientists call this material tholin, a general term for the kind of complex organic gunk that forms when you run ultraviolet light and radiation through mixtures of nitrogen and methane. Titan manufactures it continuously in its upper atmosphere. Every year, a fresh layer settles onto the surface. The dunes tell a story about Titan's wind patterns. Dunes on any world form in the direction the wind pushes them, and Titan's dunes all line up, pointing roughly east to west near the equator. That orientation told scientists something important about the global circulation of Titan's atmosphere. Near the equator, the prevailing winds blow in a consistent direction, sculpting these massive ridges into parallel lines across thousands of miles of terrain. These dunes don't move quickly. On Earth, desert sand dunes can migrate yards per year in strong winds. Titan's dunes move much more slowly, likely advancing only inches over years, driven by the infrequent strong winds that seasonal changes bring. Most of the time, the surface near the equator is calm and still. The dunes just sit there, enormous and dark, under the orange haze. What sits inside those dunes is scientifically remarkable. Each particle of dune material has been chemically processed in Titan's atmosphere, built from simple molecules reacting into more complex ones, then compressed into a solid grain by the cold and the forces acting on it during its long fall to the surface. These are not random grains of mineral dust. They carry organic chemistry built by billions of years of continuous atmospheric reactions. Some scientists describe the dune fields as an enormous preserved chemistry archive. Every grain holds a snapshot of Titan's atmospheric chemistry from the period when it formed. The layers of dune material that have built up over geological time are like chapters in a record of Titan's chemical history, stacked hundreds of feet deep across the equatorial zone. If you could scoop up a handful of that dune material and analyze it in a laboratory, the molecular complexity you'd find would be extraordinary. Scientists have recreated tholin in labs on Earth by running similar chemistry under controlled conditions. The artificial tholin they produce is brown, waxy, and chemically rich. When they expose it to liquid water, it begins to react immediately, producing amino acids and other molecules relevant to biology. Titan's surface is covered in this material. Hundreds of trillions of tons of it, spread across vast dune fields, sitting preserved in the cold. And those dunes stretch right up to the edge of the territory where something small and fragile landed in 2005. Something that sent back the first photographs anyone had ever taken from the surface of Titan. On January 14th, 2005, a small spacecraft separated from its carrier and began falling toward Titan. The probe was called Huygens, named after the Dutch astronomer who discovered Titan in 1655. It had traveled for 7 years strapped to the Cassini spacecraft, dormant for most of the journey to conserve power. On the day it released, mission controllers on Earth knew they would not be able to send any new commands. The probe was on its own. Everything it was going to do had been programmed years before. Huygens entered Titan's upper atmosphere at about 13,000 miles per hour. The friction heated its heat shield to temperatures hot enough to glow. Inside that shield, the instruments waited. Then, the atmosphere thickened around the slowing probe, and the first parachute deployed. Then, a smaller parachute. The descent began in earnest. The probe took 2 hours and 27 minutes to fall through Titan's atmosphere to the surface. During that entire descent, it transmitted data back to the Cassini spacecraft orbiting above, which relayed it toward Earth. Scientists on the ground listened in real time as Huygens fell through layers of Titan's atmosphere, measuring temperature, pressure, wind speed, and chemistry at each altitude. The data flooding in was unlike anything anyone had processed before. Then it hit the ground and survived. Scientists weren't certain Huygens would survive landing. The surface could have been a deep ocean of liquid methane, which would have swamped it within seconds. It could have struck hard, icy ground and shattered. Instead, it touched down on a surface with the consistency of wet sand or soft clay. The probe bounced slightly and settled. It kept transmitting for about 72 minutes after landing before the battery died. The images Huygens sent back from the surface showed rounded pebbles scattered across a flat, dark plain. Those pebbles looked similar to river stones on Earth. Rounded edges suggested they had been tumbled and smoothed by flowing liquid, the same process that smooths rocks in a riverbed over years of water running over them. On Titan, the flowing liquid was methane, and the rocks themselves were made of water ice. From the surface looking up, the sky glowed a pale orange. The haze diffused the distant sunlight into a soft glow that reached equally from all directions. No shadows, no blue sky, just dim orange light falling on dark pebbles and a flat plain extending to the horizon. Scientists found evidence of dried-out drainage channels nearby. The surface appeared to be a floodplain that had experienced flowing liquid in the past, possibly just before Huygens landed during a seasonal wet period, or perhaps much earlier and now dried by the equatorial climate. Huygens gave humanity its only direct look at Titan's surface from the ground. Everything else came from orbit. But that 72-minute window of data from the surface changed the conversation permanently, because some of what Huygens measured didn't quite fit the models. Things were slightly off in ways that pointed toward processes happening not just on the surface, but somewhere much deeper below it. Cassini spent 13 years watching Titan. From the time it entered Saturn's orbit in 2004 until it deliberately plunged into Saturn's atmosphere in 2017, the Cassini spacecraft flew past Titan 127 times. Each flyby brought it close enough to study the Moon's surface, atmosphere, gravity, and magnetic environment in detail. No mission before or since has spent so long, so close to any single moon. By the time Cassini finished its work, scientists had mapped most of Titan's surface with radar, measured its atmospheric chemistry at dozens of altitudes, tracked weather patterns across multiple seasons, and collected gravitational data precise enough to detect how the Moon's shape responded to Saturn's pull. That last measurement was the one that changed everything. Cassini carried an instrument designed to track tiny variations in Titan's gravity as the spacecraft flew past. Those variations came from the distribution of mass inside the Moon. A completely solid moon would have a specific gravitational profile. A moon with a layer of liquid inside it would have a different profile because the liquid can shift slightly in response to tidal forces. Saturn pulls on Titan constantly. As Titan orbits Saturn, the tidal pull from Saturn changes direction relative to Titan's body. A solid moon would flex very slightly under that force, like squeezing a rubber ball. A moon with a liquid layer inside would flex more because the liquid moves in response to the squeezing. Cassini measured Titan flexing under Saturn's gravity by about 30 feet. 30 feet of surface movement, rising and falling as Titan moved around its orbit. Scientists compared that number to what different internal models predicted. A completely solid Titan would flex by far less than 30 feet. An icy shell sitting on top of a liquid interior would flex by roughly the amount measured. The conclusion was clear. Titan almost certainly has a liquid layer beneath its outer ice shell. The liquid is almost certainly water, possibly mixed with ammonia, which lowers water's freezing point and keeps it liquid even at Titan's low temperatures. The ocean, if that's what it is, sits between the outer ice crust and a deeper layer of high-pressure ice or rock beneath it. Scientists estimate the ice shell above it ranges from several dozen to possibly over 100 miles thick. The hidden ocean is not close to the surface. Getting to it would require drilling through more ice than exists anywhere on Earth. But it's there, or very likely there. The measurement has held up through multiple analyses and is considered one of Cassini's most important findings. A moon with an atmosphere, a moon with rivers and seas, a moon with complex organic chemistry building in the sky, and now a moon with a hidden ocean buried under miles of frozen water. Each of those layers, atmosphere, surface, liquid, organic chemistry, buried ocean, adds a piece to a question that researchers hadn't originally expected Titan to raise so clearly. And the question those layers together form is one that goes beyond chemistry. But understanding the buried ocean fully required looking at why it exists at all. And that answer came from the same tidal flexing that revealed it. Saturn never lets go of Titan. The gravitational pull between Saturn and Titan runs continuously, a constant invisible force stretching across hundreds of thousands of miles of space. Titan orbits Saturn once every 15.5 Earth days. As it moves around that orbit, The angle of Saturn's pull on Titan changes constantly. The side of Titan facing Saturn feels more pull than the side facing away. That difference creates a squeezing, stretching force across Titan's entire body. On Earth, the same process happens every day. The moon pulls on Earth's oceans and crust as our planet rotates. The oceans bulge toward and away from the moon as Earth turns, creating tides. The ground also flexes slightly, though the movement is too small to feel. Scientists call the ground's response to this force a solid Earth tide. Titan experiences the same thing from Saturn, but the forces are far stronger. Saturn is enormously massive. Titan orbits much closer to Saturn than the moon orbits Earth. The tidal squeeze is powerful enough to physically deform Titan's shape by a measurable amount each orbit. Cassini measured that deformation directly. It tracked its own orbital position around Titan with extraordinary precision. When the spacecraft flew past Titan, the slight changes in Titan's gravitational pull on Cassini revealed how the moon's mass was distributed and how it was shifting. Over dozens of flybys, the pattern in that data described a moon whose outer shell was moving relative to its interior. The shell was responding to tidal forces more than a solid block of ice would. The measurement of 30 feet of surface movement was the key number. Geophysical models of Titan's interior predicted different amounts of flexing depending on what sat inside the moon. A fully solid Titan, ice from surface to core, would flex by only a fraction of what Cassini measured. A Titan with a liquid layer beneath the outer ice shell would flex by roughly the observed amount, because liquid transmits force differently than solid ice. The liquid shifts. The shell responds. That shift is how scientists confirmed the hidden ocean almost certainly exists. The moon is physically moving in a way that solid ice cannot explain alone. The ocean decouples the outer shell from the inner core. When Saturn's gravity squeezes Titan, the outer ice shell and the inner rocky core can move slightly independently, with the liquid layer between them allowing that independent motion. Think of a hard-boiled egg versus a raw egg. Spin both on a table and stop them suddenly. The hard-boiled egg stops cleanly. The raw egg wobbles because the liquid inside keeps moving after the shell has stopped. Titan's tidal response is the cosmic version of that wobble. This discovery forced a rethinking of what Titan is. A moon with an active atmosphere and hydrocarbon seas on the outside was already extraordinary. A moon with that same exterior sitting on top of a buried liquid water ocean became something else entirely. Two separate liquid environments, completely different in chemistry, separated by miles of frozen ice, both existing on the same world at the same time. The ocean beneath the ice has never been directly observed. Scientists infer its existence from indirect measurements, but the indirect evidence is strong, consistent, and built from multiple independent data sources. What that ocean might contain, and what it could mean for the possibility of life on Titan, takes the story somewhere entirely different. Something is liquid down there, miles beneath Titan's frozen surface, below the organic dunes and the river channels and the ice mountains, past the thick outer shell of frozen water that forms the crust. There is almost certainly a layer of liquid. Scientists have called it an internal ocean. The name suggests something vast and open, but the reality is more like a global layer of liquid sandwiched between two layers of solid material, pressed in from above and below, never seeing sunlight, never touching Titan's atmosphere, sealed away in permanent darkness. The liquid is almost certainly water. On a moon made largely of ice and rock, water is the most available substance that could remain liquid given the right conditions. But pure water at Titan's internal temperatures and pressures would still be frozen solid. Something has to keep it liquid. The leading candidate is ammonia. Titan formed in the outer solar system, where ammonia was abundant, and the moon likely incorporated large amounts of it into its interior during its early history. When ammonia mixes with water, it lowers the freezing point significantly. A mixture of water and ammonia can stay liquid at temperatures far below what pure water requires. Scientists believe the internal ocean on Titan is likely a dense, cold brine of water and ammonia, possibly with other dissolved compounds mixed in. The thickness of the ocean layer is unknown. Models suggest it could range from a few miles deep to potentially tens of miles. The ice shell above it is estimated to be somewhere between 30 and several hundred miles thick, depending on which calculations you use. That enormous uncertainty reflects how hard it is to probe a liquid layer sitting under miles of ice on a world nearly 1 billion miles away, using only indirect measurements from a spacecraft that never landed. Below the ocean, another layer of ice likely sits at high pressure, and below that, a rocky core. Titan is essentially a layered structure: rock at the center, then high-pressure ice, then liquid ocean, then the outer ice crust, then organic surface material and atmosphere above. Like a frozen world built from nested shells, with a liquid one hidden in the middle. The heat keeping that ocean from freezing comes primarily from radioactive decay inside Titan's rocky core. Radioactive elements release energy slowly as they break down over billions of years. That process warms the rock slightly, which warms the ice above it slightly, which keeps the base of the ocean above freezing. On Titan, with its ammonia-water mix, that small amount of warmth is enough. What the ocean looks like internally is almost entirely unknown. Scientists debate whether it is well mixed or layered by density. They debate whether material can move between the ocean and the ice shell, above it or below it. They debate whether the rocky core at the center interacts with the ocean water at all, which would matter enormously for the chemistry of the ocean itself. On Earth, where ocean water contacts rock at the seafloor, chemical reactions happen that are considered important for the origin of life. Whether any of that happens on Titan is an open question. The ocean may be chemically isolated from everything above and below it, or it may be connected in ways current instruments can't measure. The answer to that question could change everything about how scientists think about Titan, and the surface above that ocean is covered in hydrocarbons. That combination, organic chemistry on top and liquid water below, makes Titan a world with two very different reasons to look for something unexpected. Two worlds are stacked on top of each other. On the surface, Titan looks like a hydrocarbon world: methane seas, ethane rain, organic dunes made of carbon-based particles, rivers carved by liquid gas. The chemistry at the surface is entirely built from hydrogen and carbon molecules, the same family of molecules that make up oil, natural gas, and the majority of organic compounds in biology. Below the surface, separated by miles of frozen water, is a water ocean, possibly mixed with ammonia, possibly in contact with rock. A completely different kind of chemistry. Isolated from the surface by a thick, icy barrier, these two environments don't interact directly in any way scientists can currently measure. The ice shell between them acts as a wall. Organic molecules from the surface can't easily reach the water below. Water from the ocean below can't easily reach the organic surface above. The two chemistries run independently, on the same moon, at the same time, separated by a frozen barrier that may be dozens to hundreds of miles thick. That separation is part of what makes Titan so unusual. Most of the worlds scientists consider potentially habitable have one reason for interest. Europa has a subsurface ocean in contact with a rocky seafloor. Enceladus has a subsurface ocean venting actively through its crust. Titan has two distinct environments, each independently interesting, stacked together in a way that hasn't been found anywhere else. The surface chemistry is remarkable on its own terms. Complex organic molecules forming in the atmosphere and accumulating on the surface over billions of years have produced an environment rich in the kind of chemistry that preceded life on Earth. Scientists can't say those molecules are alive. Scientists can say those molecules represent a level of chemical complexity that, on Earth, eventually led somewhere significant. The buried ocean is remarkable on its own terms as well. Liquid water, even cold and salty and sealed underground, represents a potential habitat for microbial life as we understand it. The water ocean likely formed early in Titan's history and has been maintained by radioactive heating ever since. It has had billions of years to develop whatever chemistry the combination of water, ammonia, and possibly rock can produce. The combination of both, on the same world, raises a question that scientists have started taking seriously. Could material ever move between the two environments? If cryovolcanism exists on Titan, it could potentially carry ocean water upward, through the ice shell, to the surface. That water would bring with it whatever chemistry had been developing in the buried ocean. When it reached the surface, it would encounter the organic material already there. The mixing of water-based chemistry from below with hydrocarbon-based chemistry from above is the kind of event that some scientists believe could be critical for building biologically relevant molecules. On the early Earth, similar mixing between different chemical environments is thought to have played a role in setting up the conditions where life eventually emerged. On Titan, that mixing, if it happens at all, remains unconfirmed. The evidence for cryovolcanism is circumstantial. The ice shell may be too thick and too cold to allow regular exchange between ocean and surface, but the possibility alone keeps Titan near the top of every list of worlds worth studying closely. The surface chemistry is one story, the buried ocean is another, and somewhere in between those two stories, a question sits that no instrument has answered yet. Life needs water. That is one of the firmest rules in biology. Every living thing ever found on Earth requires liquid water to function. Water dissolves nutrients. Water carries chemical signals through cells. Water-based chemistry is the medium through which every biological reaction we've ever studied runs. When scientists search for life elsewhere in the solar system, looking for liquid water is the first instinct. Titan's surface lakes are not water. They're methane and ethane, chemicals that on Earth exist as gas or as industrial fuel. Standard biological chemistry, the kind that runs every cell on Earth, would instantly shut down in a lake of methane. The temperature alone, nearly 300 degrees below 0 Fahrenheit, would freeze every biological molecule known to science. But a small number of scientists have asked a different kind of question. Instead of asking whether Earth-like life could survive in Titan's lakes, they've asked whether a completely different kind of chemistry could organize itself into something that functions like life, using methane instead of water as its medium. In 2015, a pair of researchers published a theoretical blueprint for a cell membrane that could exist in liquid methane. A normal cell membrane on Earth is made of molecules that have one end attracted to water and one end repelled by it. That double-sided nature causes membranes to self-assemble in water into closed spheres, which is essentially the first step toward building a cell. The theoretical methane-based membrane these researchers described would work through similar principles, but in reverse. Instead of molecules arranging around water, they would arrange around liquid methane. The result would be a closed structure, something like a bubble, capable of holding chemistry inside it at the temperature and chemistry of Titan's lakes. The researchers were careful about what they claimed. This was a theoretical exercise, not a discovery of life. They were asking whether the physics allowed it. Their conclusion was that it did, at least on paper. Whether any chemistry on Titan has actually organized itself along these lines is entirely unknown. No mission has directly sampled Titan's lakes. No instrument has analyzed the chemistry at the shoreline of Ligeia Mare, or floated on the surface of Kraken Mare. The theoretical possibility of methane-based life on Titan's surface remains interesting precisely because it has never been tested. What scientists do know is that Titan's surface offers a unique and consistent environment. The lakes have been there for a long time. The temperature is stable. The organic chemistry raining down from the atmosphere provides a continuous supply of complex molecules. If chemistry were going to organize itself in methane-based ways anywhere in the solar system, Titan's lakes would be a reasonable place to look. The Dragonfly mission, planned to arrive at Titan in 2034, won't land in the lakes. It will explore the surface near the equatorial dune fields and a region where a large impact crater sits. But some of the chemistry it will measure on the surface may reflect what has been building in and around the lakes for billions of years. A second kind of potential life on Titan, sitting in the buried water ocean miles below the surface, operates under completely different rules. And that possibility is where the story gets even more complicated. Titan forces scientists to hold two completely different conversations at the same time. The first conversation is about what's happening on the surface. Organic molecules falling from the sky, complex hydrocarbons building up over billions of years, methane lakes sitting under active cloud systems. The chemistry of the surface is alive in the sense that it keeps changing, keeps building, keeps producing new molecules. It's the largest natural organic chemistry laboratory in the solar system. The second conversation is about what might be happening underground, a liquid water ocean possibly in contact with rock, stable for billions of years, warmed by radioactive decay, chemically isolated from the surface above it. The conditions inside that ocean resemble, in some ways, the environments on Earth where life has been found in places previously thought to be completely inhospitable. The surface story and the underground story don't share much overlap. They're happening on the same world, separated by miles of ice, running on entirely different chemistry, driven by entirely different energy sources. Combining them into a single description requires treating Titan as two separate worlds that happen to occupy the same moon. Astrobiologists, scientists who study the conditions that might support life, have been careful about how they frame Titan. The moon is not a place where life is expected. It's a place where two independent environments each offer a different reason to look more carefully, and where the combination of both, stacked together, makes the overall picture more interesting than either one alone would be. The surface chemistry is relevant to one of the oldest questions in biology. How did life start? Before the first cells existed on Earth, chemistry had to get complicated enough to organize itself. The exact steps between simple chemistry and the first self-replicating molecule are still debated. Titan's surface represents a real-world version of a prebiotic chemical environment, one that researchers can study without the complication of biology already having changed everything. On early Earth, similar organic chemistry was running in the atmosphere and oceans before life emerged. Scientists can't run that experiment again on Earth. Titan may offer the closest available version of what a prebiotic world looks like after billions of years of continuous chemistry. Not an Earth analog, a chemistry analog, the underground story fits a different set of questions. On Earth, life has been found in deep ocean hydrothermal vents where liquid water contacts hot rock. It's been found in deep underground aquifers sealed from the surface for millions of years. Life on Earth has pushed into every stable liquid water environment it could reach. Whether life has pushed into any stable liquid water environment on Titan is something no instrument has ever tested. The two stories also offer a troubling possibility. If life were present in Titan's buried ocean and found a way to reach the surface through cryovolcanism, the organic chemistry at the surface would be a potential food source. Organic material raining down from the atmosphere, combined with upwelling ocean water, could in principle support a surface chemistry that goes beyond what simple molecular reactions produce. This is far from established. The scenarios involved require multiple things to be true simultaneously. But the fact that multiple things being true simultaneously on Titan is within the range of what the evidence allows is exactly what keeps scientists coming back to this moon. 4 billion years ago, Earth had no life. The atmosphere was a thick mixture of nitrogen, methane, carbon dioxide, and other gases. No oxygen to breathe. No ozone layer to block ultraviolet radiation. Sunlight hit the early atmosphere directly and broke apart molecules near the top. The products of that chemistry drifted down and mixed with a surface covered in water, both in shallow pools and in deep oceans. Somewhere in that environment, chemistry organized itself into something that could copy itself. The exact moment, the exact location, and the exact molecular steps are still debated by scientists, but the starting conditions are better understood. Simple molecules, energy from sunlight or hydrothermal vents, liquid water as a medium, and time, an enormous amount of time, Titan shares several of those starting conditions in a modified form. The atmosphere is primarily nitrogen, same as early Earth's. Methane is abundant in both. Ultraviolet radiation breaks apart molecules in the upper atmosphere of both worlds. The products of that chemistry build into more complex organic molecules. Those molecules accumulate on the surface over long periods. The key difference is liquid water. Early Earth had it abundantly at the surface. Titan has it only deep underground. On the surface, Titan replaced water with methane. That replacement changes the chemistry significantly. Many of the reactions that matter for biology require water as a solvent. Methane does not dissolve the same compounds in the same ways. But the atmospheric chemistry, the part that happens before any molecule reaches the surface, shows stronger parallels. When scientists create tholin in laboratories by running energy through nitrogen-methane mixtures, the products include amino acids when water is later added. Amino acids are the building blocks of proteins. Proteins are among the core molecules of life on Earth. Finding that tangent-like atmospheric chemistry can produce amino acid precursors when exposed to water suggested that the chemical road from simple gases to biologically relevant molecules might be shorter and more universal than once thought. Those laboratory results don't prove anything about Titan. They show that the chemistry is capable, under the right conditions, of producing molecules that matter. Whether those conditions exist on Titan's surface or in its buried ocean is a separate question. The deeper connection between Titan and early Earth is conceptual. Both worlds ran extended experiments in prebiotic chemistry. Earth's experiment eventually produced life. Titan's experiment has been running for roughly the same amount of time, in a colder and differently mixed environment, without water at the surface. Comparing the products of both experiments could tell scientists what role each specific condition played. On Earth, scientists can't observe early prebiotic chemistry directly. It happened before life existed, and life itself changed the surface and atmosphere so thoroughly that the original conditions are gone. Titan preserves something closer to a frozen version of that early state. The organic chemistry on Titan has been building for billions of years without life rearranging it. That makes Titan a reference point, a place to study what chemistry alone, given time and energy, and the right molecules, can produce. The answer to that question might clarify which steps in the origin of life were chemistry and which required something additional. And below all that surface chemistry, a geological process may be the key to whether any of those molecules ever reached liquid water at all. Something may be pushing upward from below. On Earth, volcanoes exist because the interior is hot enough to melt rock. That molten rock, called magma, rises through cracks in the crust and erupts at the surface as lava. The process reshapes landscapes, releases gases into the atmosphere, and connects the deep interior of a planet to everything above it. On Titan, the interior is cold by Earth standards. Solid water ice forms the crust. The ocean below it is liquid water and ammonia, far below the freezing point of water on Earth, but liquid because of the ammonia mixed in. Deep beneath that, a rocky core generates mild heat from radioactive decay. Under the right conditions, the pressure and heat in Titan's interior could force a mixture of water, ammonia, and methane upward through cracks in the icy crust. When this cold, slushy mixture reaches the surface and erupts, scientists call it cryovolcanism. Cryo meaning cold, volcanism meaning the process of interior material reaching the surface. Several features on Titan's surface have been studied as potential signs of cryovolcanic activity. Cassini's radar and infrared instruments identified regions where the topography looked unusual, places where material seemed to have flowed and solidified in ways that surface erosion or wind couldn't easily explain. One area called Sotra Patera has a shape resembling a volcanic crater with what appear to be flow features extending from it. Some scientists have argued these features point toward cryovolcanic origin. The debate has not been settled. Other scientists argue the same features could have formed through impact processes, tectonic shifting of the ice shell, or erosion patterns that just happen to look volcanic. Without landing nearby and sampling the material directly, the argument remains open. What makes cryovolcanism important for Titan's story goes beyond surface geology. If cryovolcanism is active, it connects the interior ocean to the surface. Water and ammonia from the buried ocean would vent upward, reach the surface, and encounter the organic chemistry waiting there. The two environments, the hydrocarbon surface and the water interior, which otherwise sit separated by miles of frozen ice, would briefly mix at eruption sites. That mixing matters because of what each environment brings. The surface has complex organic molecules built over billions of years of atmospheric chemistry. The ocean water carries dissolved minerals, ammonia, and possibly products of water-rock interaction from deep below. When those two chemistries meet, the range of possible reactions expands dramatically. On Earth, hydrothermal vents at the seafloor are considered one of the most promising environments for the origin of life, precisely because they mix hot mineral-rich water with the organic chemistry of the surrounding ocean. Titan's cryovolcanic sites, if they exist and if they're active, would be a cold temperature version of a similar mixing event. The methane source problem from earlier also connects here. If cryovolcanic processes push methane upward from the interior, they could be resupplying Titan's atmosphere with the methane that radiation keeps destroying at the top. The interior would act as a slow reservoir, releasing fresh methane to the surface and then to the atmosphere over geological timescales. Whether cryovolcanism is happening on Titan today is one of the most important unanswered questions the Dragonfly mission may help address. Certain surface materials, if found near features that look volcanic, could confirm past or present activity. The next mission to Titan is coming. But getting to that point required understanding just how strange Titan's calendar is. Titan moves slowly through time. One orbit around the Sun takes Saturn 29.5 Earth years to complete. Titan orbits Saturn, so Titan's year lasts the same length. Summer on Titan lasts about 7 Earth years. Winter lasts about 7 Earth years. The transitions between seasons are long, gradual, global shifts that reshape the weather patterns of an entire moon over periods longer than a human lifetime. On Earth, seasons change because our planet is tilted. The northern hemisphere leans toward the sun in summer and away in winter. The same principle applies to Titan, since Titan's orbit is tilted relative to the sun's equatorial plane. As Titan moves through its year, the amount of weak sunlight reaching the northern hemisphere changes. So does the distribution of clouds, rain, and evaporation. Scientists studying Titan with Cassini watched it move through roughly half of one full Titan year. During that time, the cloud patterns changed. Early in the mission, significant cloud activity appeared near the South Pole. As the years passed and the season shifted, cloud activity in the south quieted and signs of increasing activity in the north picked up. The northern cloud systems that Webb and Keck observed in 2022 and 2023 were part of that ongoing seasonal progression. Northern summer was underway, and the northern hemisphere was responding. The most direct effect of seasonal change on Titan involves the lakes and seas. During northern summer, increased sunlight drives stronger evaporation from the northern seas, pushing more methane into the atmosphere and feeding the cloud convection that Webb detected. The seas themselves may change level over seasonal cycles as rainfall replenishes them during different periods. In the southern hemisphere, the smaller lakes that Cassini observed have shown signs of shrinking over time. As the south moves toward winter, less sunlight reaches it, temperatures drop further, and clouds that once brought rain to the south become rarer. The liquids evaporate more slowly, but rainfall also decreases, and the net result appears to be a slow draining of the southern lakes. This seasonal asymmetry raises a long-term puzzle. If the south is losing liquid and the north is gaining it over one Titan year, What happens when the seasons reverse? Does the south refill? Does the north drain? Scientists believe the overall system is roughly in balance over full cycles, but the exact dynamics are still being worked out. The data from Cassini only covers part of one Titan year, and Webb observations add more recent points, but don't extend the baseline far enough to see a complete cycle. The long seasons also mean that any mission to Titan lands in a specific seasonal context that will persist for years. When Dragonfly arrives in 2034, northern summer will still be ongoing. The northern cloud activity, the active methane cycle, the weather patterns that Webb observed will all still be running. Dragonfly will land during an active period in Titan's weather history. But Dragonfly won't land in the north. It will land near the equator, in the dune fields and near a specific crater that scientists believe preserves something important. Something that connects Titan's chemistry to a question no spacecraft has ever answered directly. It has been snowing on Titan for 4 billion years. The snow is not water. It falls in particles too small to see individually, drifting downward through hundreds of miles of atmosphere at a pace so slow the journey takes months. Each particle carries complex organic chemistry built in the upper atmosphere from the simplest possible starting materials. Nitrogen and methane, broken apart by radiation, reassembled into something far more complicated. The process starts near the top of Titan's atmosphere, over 200 miles above the surface. At that altitude, radiation and sunlight break methane and nitrogen molecules apart. The fragments react with each other. They build into small organic molecules. Then those molecules react further into larger ones. The products grow heavier. They clump together into particles just large enough to start falling slowly under Titan's gravity. As those particles descend, they pass through different layers of atmosphere. At each layer, the temperature and chemistry change slightly. Particles collide with other molecules, picking up new chemical attachments. Some particles combine with others, growing larger. By the time they reach the lower atmosphere, they've spent months traveling through a chemical processing zone that added complexity at every stage. The result is tholin, that dark, reddish-brown organic material that covers the dunes and coats the surface of Titan in a thin layer everywhere the dunes don't dominate. Tholin is not a single molecule. It's a complex mixture of hundreds or thousands of different organic compounds, each one produced somewhere in the long descent through the atmosphere. The mixture varies slightly depending on where and when it formed, but the overall chemical richness stays consistent. Scientists have analyzed tholin produced in laboratory experiments and found extraordinary complexity. When they expose lab-made tholin to liquid water, it reacts immediately and produces a range of biologically relevant molecules. Some experiments have detected nucleobases, the chemical components of DNA and RNA, forming from tholin under certain conditions. Again, scientists are careful about conclusions. Finding nucleobase precursors doesn't mean Titan has DNA. It means the chemistry capable of producing those compounds is running on Titan's surface continuously. The total amount of organic material deposited on Titan's surface over its history is staggering. Scientists estimate the surface layer of tholin and related compounds could be hundreds of yards thick in some areas, possibly much more in regions that have been accumulating material for the longest time. Titan's dune fields may represent the most densely packed organic chemistry archive in the solar system outside of Earth itself. That archive is also exceptionally well preserved. The extreme cold of Titan's surface slows chemical reactions dramatically. Organic molecules that would break down in hours under warmer conditions can persist on Titan's surface for enormously long periods. The cold acts as a freezer, keeping the chemistry stable and intact, waiting for something to change the conditions. What could change those conditions is the question. Water is the obvious answer. Water from cryovolcanic activity, or water from an impact that melted surface ice, would instantly start reacting with the tholin beneath it. The range of products from that kind of mixing experiment running for even a brief period on Titan's surface could be extraordinary. Whether that mixing has ever happened and what it produced when it did is something only a surface mission could investigate. And that mission is already being built. The ice is in the way. Between Titan's organic-rich surface and the buried water ocean below lies a shell of frozen water estimated to be dozens to possibly hundreds of miles thick. That shell is the barrier separating the two most interesting chemical environments on the Moon. Whether anything has ever crossed it in either direction is one of the most argued questions in Titan science. For material to move from the surface down to the ocean, it would need to travel through miles of solid ice. On Earth, some materials can migrate slowly through ice over geological timescales. Water itself can refreeze around organic molecules and pull them slightly deeper, but the distances involved on Titan make direct surface-to-ocean transport implausible under normal conditions. The organic molecules raining down from the sky are landing on top of a very thick, very cold, very solid barrier. The more plausible pathway runs in the other direction, from the ocean upward. If cryovolcanism exists and is active, ocean water pushes up through the ice shell and reaches the surface. When that water arrives, it encounters the organic material waiting above. The mixing happens at the surface, not in the middle of the ice. The ocean doesn't need to receive organic material. It needs to deliver its water to the organics above. Whether even that pathway exists is still being debated. The evidence for cryovolcanism on Titan is unconfirmed. The ice shell may be thick enough and cold enough to prevent any active exchange between ocean and surface. In that case, the two environments are genuinely isolated from each other, running their separate chemistry without ever interacting. Some scientists have proposed a middle scenario: impact events, where meteorites or comets hit Titan's surface can generate enormous amounts of heat very quickly. A large impact melts the ice beneath and around it, temporarily creating a pool of liquid water at the surface. That liquid water sits surrounded by organic material on the surface and ice beneath. The pool lasts for thousands to tens of thousands of years before freezing over again. During that window, water and organic chemistry mix. The range of reactions possible in a warm, liquid water environment surrounded by tholin is extensive. Amino acids, nucleobases, and other biologically relevant molecules have been produced in laboratory simulations of exactly this kind of impact melt chemistry. On Titan, where large impacts have certainly occurred over 4 billion years, multiple such events may have created temporary liquid water environments at the surface. Titan has at least one confirmed large impact crater that scientists consider particularly significant. Selk Crater, a structure roughly 50 miles wide near Titan's equator, is the landing zone for the Dragonfly mission. Dragonfly will land near and inside Selk Crater specifically because scientists believe the impact that created it would have melted ice and mixed water with the surrounding organics. The products of that chemistry may still be preserved in the cold surface material around the crater. The mixing that might take seconds in a laboratory happened at Selk Crater over thousands of years. If that extended mixing event produced anything chemically significant, the evidence may be sitting right there in the surface material, frozen and intact, waiting for a robotic lander to scoop it up and analyze it. Titan builds things. Every day, in the upper atmosphere of that distant orange moon, sunlight and radiation break simple molecules apart. Every day, the fragments of those broken molecules find each other and combine. Every day, the products of those combinations drift slowly downward, growing more complex with each layer they pass through. Every day, material settles onto the surface and adds to a chemical archive that has been accumulating for billions of years. The scale is hard to grasp. Titan is about 4,000 miles across, roughly the width of the continental United States. Its atmosphere extends hundreds of miles above the surface. The entire volume of that atmosphere is an active chemical reactor. Every cubic mile of it is producing organic molecules continuously. The surface area catching the fallout from that reactor is larger than all of North and South America combined. On Earth, organic chemistry at this scale exists only because of life. Living organisms produce and process organic molecules continuously, covering every ecosystem. Before life existed, Earth's prebiotic chemistry was far more limited in scope. On Titan, complex organic chemistry runs at planetary scale without any biology driving it. Pure atmospheric reactions, powered by sunlight and Saturn's radiation, are building molecular complexity across an entire world. Scientists studying the origin of life care deeply about what this means. One of the hardest questions in biology is how chemistry becomes biology. Going from simple molecules to a self-replicating molecule capable of evolution is a transition that requires specific conditions. Whether those conditions are common or rare in the universe is unknown. Titan suggests that the early steps, building complex organic molecules from simpler starting materials, can happen on an enormous scale under conditions that are probably common in the outer solar system. Titan's chemistry is not unique to Titan. Nitrogen and methane are among the most abundant molecules in the cold outer solar system. Other moons, other distant worlds, may run similar chemistry at their surfaces or in their atmospheres. Titan is the most accessible example, the one with a thick enough atmosphere and the right combination of factors to make the process visible from a distance and eventually reachable by spacecraft. If complex organic chemistry is a natural product of nitrogen-methane environments hit by radiation, and if such environments are common in the outer solar system and in planetary systems around other stars, then the raw material for life may be extraordinarily widespread. Titan doesn't prove life is common. It proves that one of the key prerequisites for life, rich organic chemistry, can build up on a massive scale under conditions that don't require proximity to a star. That reframing matters. For decades, the search for life focused on the habitable zone, the region around a star where liquid water can exist on a planet's surface. Titan sits far outside any normal habitable zone. It has no liquid water at its surface, yet it carries one of the most chemically rich environments in the solar system. The ingredients for life may not need a warm, sunny location. They may need only time and the right mix of simple molecules. Titan has had both, and a robotic spacecraft, currently being built on Earth, is going to land there in less than a decade to see exactly what 4 billion years of planetary-scale chemistry has built. A helicopter is going to fly on Saturn's moon. That sentence sounds impossible until you understand Titan's atmosphere. Most moons have no air to fly through. Titan has an atmosphere 4 times denser than Earth's at sea level. Its gravity is about 1/7 of Earth's. Those two facts combine to make flight on Titan far easier than flight on Earth. A rotorcraft designed for Titan needs to generate far less lift to stay airborne. The thick air and weak gravity do most of the work. Dragonfly is the spacecraft NASA is building to take advantage of that. It carries 8 rotors arranged in pairs, like a large drone. On Earth, a similar structure with the same power output would barely lift off the ground. On Titan, with 4 times more air to push against and 1/7 the gravitational pull, the same design can carry a full scientific payload and fly for miles. The mission is powered by a radioisotope thermoelectric generator, the same technology that powered Cassini and Curiosity. A small amount of radioactive plutonium produces steady heat, and that heat gets converted into electricity. The system generates power continuously, regardless of sunlight or weather, which makes it ideal for Titan's dim, haze-filtered environment. Solar panels on Titan would produce almost nothing useful, given how little light reaches the surface. Dragonfly's basic method of operation involves landing, spending days to weeks at one location doing science, then flying to the next location. Each flight could cover several miles over the planned mission lifetime. Dragonfly expects to travel farther across Titan's surface than the Mars rovers have traveled across Mars in their combined decades of operation. The landing sites are chosen for scientific value. Dragonfly will start near the Shangri-La dune fields in Titan's equatorial region, studying the organic material there. It will then work its way across the surface towards Selk Crater, the Large Impact Site, where scientists believe water and organics mixed after the impact that formed it billions of years ago. Along the way, Dragonfly will sample the surface chemistry at each location. It carries instruments capable of identifying specific molecules, measuring the isotopic composition of materials, and analyzing what the surface is made of at a level of detail no orbiting spacecraft can achieve. The difference between Dragonfly and everything that came before it is the difference between photographing a painting from across a room and holding it 6 inches from your face under a bright light. Flying between sites lets Dragonfly cover the kind of scientific diversity that a fixed lander could never reach. Different terrain types, different surface compositions, different proximity to lakes and dunes and craters. Each location tells a different part of Titan's story. The combined dataset from all those sites will be richer than any single landing could produce. NASA is targeting a launch in 2028. The journey to Titan takes about 6 years. Dragonfly is scheduled to land in 2034. When it does, it will carry scientific tools capable of finding exactly the kind of molecules that would indicate whether Titan's billions of years of chemistry ever crossed the line towards something more. Landing is just the beginning. When Dragonfly touches down on Titan's surface, the first thing its instruments will do is take stock of the ground beneath it. What molecules are present? How complex are they? How do the compositions differ from one landing site to the next? Those questions drive the mission's entire scientific program. The primary target is prebiotic chemistry, molecules that, on Earth, appeared before life and are considered relevant to how life started. Amino acids, the building blocks of proteins. Nucleobases, the components of DNA and RNA. Fatty acids, and other molecules capable of forming membranes. These compounds are the chemical prerequisites for biology as we know it. Whether Titan's surface contains them in significant quantities is one of the central questions Dragonfly will try to answer. The instruments on board include a mass spectrometer capable of identifying individual molecules by their weight and structure. When Dragonfly samples a piece of surface material, the spectrometer breaks it apart and measures the fragments, essentially reading a molecular fingerprint. The level of detail is far beyond what any remote telescope observation can achieve. Webb can detect that certain types of molecules exist in Titan's atmosphere. Dragonfly can identify specific compounds on the ground and tell you exactly what they are. Selk Crater is the geological centerpiece of the mission. The impact that created it was large enough to melt the ice beneath the surface and mix it with the surrounding organic material. That mixing event created a temporary liquid water environment surrounded by tholin, the rich organic material that coats Titan's surface. Scientists believe the products of that chemistry, whatever formed when hot water met the organics during and after the impact, may still be frozen in the surface material around the crater. If Dragonfly finds complex organic molecules at Selk that are more chemically advanced than the surrounding dune material, that would be strong evidence that impact-driven water-organic mixing produced something new. If those molecules include amino acids or nucleobases, the implications for the origin of life chemistry would be significant. Dragonfly will also measure the isotopic composition of carbon and nitrogen in the surface materials it samples. Isotopes are versions of the same element with different masses. On Earth, biological processes preferentially use certain isotopes over others, creating a chemical signature that scientists call a biosignature. If Titan's surface shows similar isotopic patterns, that would raise questions worth asking very carefully. Scientists are realistic about what Dragonfly will find. The most likely result is a rich and detailed picture of prebiotic chemistry, evidence that the organic factory in Titan's atmosphere has been delivering complex molecules to the surface for billions of years, and clues about what happens when those molecules encounter water. That result alone would transform the field of astrobiology. Finding direct evidence of biology would be an extraordinary result that nobody is betting on. But the mission is designed to answer questions that no other spacecraft has been positioned to ask. And while Dragonfly investigates the surface, a broader question will hang over every measurement it takes. A question about time, about how long Titan can keep running the experiment it's been running. The clock Webb started is still running. Every measurement Webb made of Titan's atmosphere confirmed that the chemistry is active, the methane cycle is running, and the organic factory is producing. But those measurements also made a long-standing problem sharper. Methane is leaving Titan's atmosphere continuously, broken apart by radiation and converted into heavier molecules that settle to the surface. The hydrogen escapes into space. The methane is not coming back. Webb's detection of methyl radical confirmed that this destruction process is happening right now at the rate models predicted. That's the confirmation scientists needed. It also confirmed that unless something is replacing the methane being destroyed, the supply is finite. The clock is ticking. How long Titan keeps its atmosphere depends entirely on the methane source. If cryovolcanism is actively pushing methane up from the interior, the supply could last far longer than the surface reserves alone would allow. If the interior methane source is weak or absent, Titan's atmosphere faces a slow wind down over tens to hundreds of millions of years. During that wind down, the changes would be gradual. The thick haze would thin. The cloud systems would become less active as methane evaporation from the seas slowed. The seas themselves would shrink as methane escaped to the atmosphere and then to space faster than they were refilled. The rivers would run less frequently. The organic snowfall from above would slow as the atmospheric chemistry lost its fuel. Eventually, if nothing replenishes the methane, Titan would become a colder, drier, quieter place. The thick atmosphere that makes it so unusual among moons would gradually give way. What remained would be a moon covered in a deep layer of organic material with a thin nitrogen atmosphere, small remnants of liquid in the polar regions, and a buried ocean still intact beneath the ice, completely isolated from the now quiet surface above. The transition from active Titan to quiet Titan would take longer than humans have existed as a species. It would take longer than recognizable human civilization would be expected to last. On those timescales, Titan would be fine. But on geological timescales, the question is real. Webb cannot answer it directly. Detecting that methyl radical exists confirms the destruction process. Determining the rate of replenishment from the interior requires measurements that Webb cannot make from orbit. It requires either a seismometer on Titan's surface, which could detect internal activity, or direct sampling of volcanic material, or long-term monitoring of the atmosphere's methane content over decades. Dragonfly will contribute some data relevant to this question, particularly through measurements of isotopic ratios that could distinguish between ancient methane from the interior and more recently cycled methane. But a definitive answer will likely require missions beyond Dragonfly, possibly including an atmospheric probe or a lander capable of measuring the composition deep below the surface. For now, Titan's atmosphere runs on, and the question of how long runs with it. Two other moons in the outer solar system are also competing for attention, and comparing Titan to its closest rivals reveals exactly how unusual this frozen orange world really is. 3 moons are competing for the same title. Europa orbits Jupiter, Enceladus orbits Saturn, Titan orbits Saturn. All 3 have subsurface liquid water oceans. All 3 are considered priority targets for astrobiology. All 3 have been studied intensively by spacecraft. But they are very different places, and the ways they differ tell a story about what makes each one potentially significant. Europa is the simplest case, in a specific sense. Its ocean is vast, potentially deeper than any ocean on Earth, and sits in direct contact with a rocky seafloor. That contact between liquid water and rock, especially in the presence of heat from tidal forces generated by Jupiter, creates conditions similar to deep-sea hydrothermal vents on Earth. Those vents are among the most productive biological environments on our planet. Europa's ocean gets most of its scientific attention because the ocean-rock interface is considered one of the most promising environments for life in the solar system. But Europa's surface is almost chemically bare. It has very little organic material compared to Titan. Whatever chemistry is happening in Europa's ocean has been running without an external source of organic compounds raining down from above. The ingredients for complexity may be limited to what formed internally. Enceladus is smaller and wilder. Its ocean actively vents to space through cracks at the South Pole. Geysers shoot water vapor and organic molecules hundreds of miles into space, forming a ring of material around Saturn. The Cassini spacecraft flew through those plumes and directly sampled the chemistry. Scientists found organic molecules, silica particles suggesting hot water rock interaction, molecular hydrogen indicating active geochemical reactions, and salts pointing to a liquid ocean in contact with a rocky floor. Enceladus essentially presents its ocean chemistry for direct analysis without requiring a lander or a drill. That accessibility is remarkable. The chemistry in those plumes includes everything scientists look for when assessing whether an environment could support life. No other world in the solar system offers that kind of sampling opportunity from a simple flyby. Titan's advantage over both is the surface. Neither Europa nor Enceladus has a chemically rich surface. Neither has an atmosphere generating complex organic molecules. Neither has a complete weather cycle. Titan's surface is the richest chemical environment in the outer solar system, and that surface chemistry has been building for billions of years. The combination of surface organic chemistry and a buried water ocean is unique to Titan. The disadvantage Titan carries is depth. Enceladus puts its ocean chemistry in front of you. Europa's ocean may be reachable through a future drilling mission. Titan's ocean sits under a crust that may be over 100 miles thick. Getting to it is beyond any technology currently planned. So the three moons address different questions. Enceladus is the best place to sample ocean chemistry from space. Europa is the best target for a future ice-penetrating mission. Titan is the best place to study prebiotic chemistry on a surface and to understand what complex organic environments look like after billions of years of continuous chemical building. Each one important, each one different, and together they form an argument for the outer solar system being far more biologically relevant than anyone expected when the space age began. Titan just made the universe more crowded with possibilities. For most of human history, the search for life beyond Earth focused on places that looked like Earth, planets close to their stars, planets with liquid water on the surface, warm, well-lit worlds where biology as we know it could run without modification. That search was sensible given what we knew. It was also narrow, given what we've since learned. Titan breaks every assumption that search was built on. It sits nearly 900 million miles from the Sunday. Its surface temperature is nearly 300 degrees below 0 Fahrenheit. Its lakes are liquid natural gas. Its mountains are frozen water. Its rain is flammable. By every standard developed for searching Earth-like life in Earth-like places, Titan should be crossed off the list. Instead, it's near the top of the list of most interesting worlds in the solar system. The reason comes back to organic chemistry. Life on Earth is built from organic molecules. The steps that led to life on Earth began with organic molecules forming in the atmosphere and oceans of a young planet. Titan shows that those steps, the formation of complex organic molecules from simple starting materials, can happen at enormous scale in an environment radically different from early Earth. Different temperature, different chemistry at the surface, far from the Sunday. If complex organic chemistry can happen at Titan's scale in those conditions, the implication for the universe is significant. Nitrogen-methane environments exist throughout the solar system and are likely common around other stars as well. The outer regions of planetary systems, where cold worlds orbit their stars at large distances, may routinely develop the kind of atmospheric chemistry Titan demonstrates. The organic material that chemistry produces may be widespread. That doesn't mean life is widespread. Organic chemistry is a necessary condition for life, as we understand it, not a sufficient one. Titan's surface may hold billions of years of complex organic chemistry and still be completely lifeless. The gap between chemistry and biology remains one of the most important unsolved problems in science. But Titan demonstrates that the chemistry side of that gap is not the limiting factor. Building complex organic molecules from simple gases does not require a warm planet close to a star. It requires radiation, the right molecules, and time. All three are available across enormous regions of every planetary system. The detection of methyl radical by Webb confirmed that a specific, critical step in this chemistry is actively running on Titan. Catching that intermediate molecule, the bridge between simple methane and complex organics, showed that the process is live, verifiable, and traceable from a distance. Other telescopes can now search for similar chemistry in the atmospheres of moons and planets around other stars. Using the same approach Webb applied to Titan, the universe is full of nitrogen-methane environments. Saturn's largest moon just told us what happens in those environments over billions of years. The answer is rich, complex, continuous organic chemistry, building toward something. Whether that something has ever crossed the line toward biology on Titan or anywhere else in the cold outer regions of a solar system is the question that will drive planetary science for the next century. Titan didn't answer the question of whether life exists beyond Earth. It made the question harder to dismiss. Everything we've sent to Titan has changed the conversation. Pioneer 11 flew through the Saturn system in 1979 and gave scientists their first close look at a world they'd only seen through telescopes. Cassini spent 13 years in Saturn's orbit and transformed Titan from a mysterious orange sphere into a world with mapped terrain, confirmed lakes, measured weather patterns, and a probable buried ocean. Huygens landed on the surface and sent back images no human eye had ever seen from that place. Webb added chemistry, confirmed molecules, active atmospheric processes caught in real time, the middle steps of reactions that had been theorized for decades but never directly observed. Each mission added a layer. Each layer made the next question clearer. Dragonfly is the next layer. When it arrives in 2034, it will bring something none of its predecessors could offer: the ability to move, land, sample, and move again. The combination of surface access and mobility will produce a picture of Titan's chemistry more detailed than anything achievable from orbit. The landing sites are chosen to maximize the scientific return. Dragonfly will operate in Titan's equatorial zone for years, flying from dunes to craters to plains, measuring what each environment has built over geological time. After Dragonfly, the future missions to Titan are not yet designed. Scientists have proposed several concepts: a floating buoy that could sit on the surface of Krakenmare and analyze the composition of the methane sea, a submarine capable of diving beneath the surface of a Titan lake and measuring what sits in the depths, a probe capable of penetrating the ice crust to sample the buried ocean directly, though that last concept remains far beyond current technology. Each concept would answer questions that no current mission can reach. The composition of Titan's seas, measured in situ rather than inferred from orbit, would settle debates about the chemistry at the liquid surface. A sample from below the ice would be among the most scientifically significant measurements ever made anywhere in the solar system. What makes Titan the most important unvisited world, in terms of raw scientific stakes, is the combination of timescales. 4 billion years of continuous organic chemistry, uninterrupted by plate tectonics, biological activity, or significant atmospheric loss. The record of that chemistry may be preserved on the surface in layers of tholin and organic sediment, available for analysis if the right instruments land in the right places. On Earth, the early chemical record is gone, overwritten by biology and geology over billions of years. On Titan, the cold has preserved it. The organic archive on Titan's surface may be the closest thing in the solar system to a recording of what prebiotic chemistry does when left alone, given time, given energy, and given no biology to interrupt it. Scientists approaching the question of life's origin on Earth are missing the early chapters. The chemistry that happened before the first cell existed left almost no trace on our planet. Titan may hold those chapters frozen in the surface, waiting. The James Webb Space Telescope caught a single molecule in Titan's upper atmosphere, a fragment, a flash, gone in seconds, but detected before it disappeared. That detection was one thread pulled from a vastly larger fabric. The fabric is an entire world built from organic chemistry, running for 4 billion years, 900 million miles from the sun, under a sky the color of fire. We have touched the edge of it. What waits in the rest is a question that will outlast every telescope we've ever built.